The next idea we need to talk about is called differentiability, which is a way of saying where does a function have a derivative, the slope of a tangent line, and where can we not find the derivative, the slope of a tangent line. There are three ways that a function can be non-differentiable at a particular x value. Ways a function can be non-differentiable at x equals c. Three ways that we could have a problem with finding a slope. Three ways we could have an issue. For starters, you have to be continuous to be able to find a slope. I can find a slope anywhere over here, but right at x equals c, I can't talk about finding the slope of a tangent line. Not going to work. Our first issue is we could have a discontinuity, and any type of discontinuity would work. If I have a jump, a vertical asymptote, a hole, any of those, I'm not going to have a derivative at x equals c. But there are ways that I could be continuous and still not have a slope, still not have a derivative. And one of these I feel like we saw in the very first video on derivatives. What if I give you an absolute value function that kind of looks like that? I'm continuous. I can trace out this thing without picking up my pencil or go through the limit definition of continuity and all those things. But the deal is, at x equals c, well, to the left of x equals c, the slope is some constant positive. But to the right of x equals c, the slope is some constant negative. And at c, it suddenly changes from maybe like a slope of positive 1 to a slope of negative 1 or something like that. I have what I'm going to call a sharp turn, also sometimes referred to as a cusp. Your bicuspids are sharp teeth in your mouth. Cusp, something sharp. If we have a sharp and sudden turn, we're not going to be able to find a derivative there. Now, if I have a graph like this, that's not a sharp turn. Could I find my derivative at that point? And if so, what is the derivative? The derivative right there, that's 0. And I've got a gradual change from positive values to less steep positives, closer to 0, closer to 0, 0, then a small negative, a bigger negative, and so on over there. It was a gradual change. That's perfectly okay. So I think I'm going to cross that out because I don't want you confusing that with a sharp turn. I need something like this, or something like that, or whatever. Third way. What if I have something that looks kind of like that? Perfectly continuous. I don't have a sharp turn. It's very smooth over there. But what's going on with a tangent line at x equals c? Maybe this wasn't the absolute best drawing, but I think my tangent line is vertical. I have a vertical tangent. The point is, go back to algebra 1 for a minute. What's the slope of a vertical line? Yeah, undefined. If a tangent line has a vertical slope, if a tangent line is vertical, that means its slope is undefined, which means its derivative is going to be undefined. There are three things we need to be able to look for. So I'd like to take a moment and take a look at that worksheet you have in your packet of in-class things, titled In-Class Practice with Graphical Derivatives and Differentiability. And we're going to jump all over this worksheet. I would like to start on the back, and I'd like to look at number 33. We need to figure out all the places where that function is not differentiable. Take a moment and do that. Push pause if you're watching on YouTube, or Edpuzzle will just stop, and you're going to tell me where that function is not differentiable. Let's see, x equals, how about I just sort of go from left to right here? I see we're not continuous over there. 1, 2, 3. X equals -3 is a place we are not differentiable. I think x equals -1 is a place we're not differentiable because we're not continuous there. I think 1, 2, 3, x equals +3 is also a place we're not differentiable because we're not continuous. Really, I was just looking for places where I wasn't continuous on this one. I didn't have any sharp turns. I don't think I had any vertical tangents. We're just going to go with those 3 options. Try number 34, and I promise it's more than just where we're not continuous. See if you can figure out where 34 is not differentiable. Okay, well, I see a sharp turn over here at x equals -2. I see a discontinuity at x equals 3. And I think that'll do it. X equals -2 and 3. Let's go down to 35. I want to know where that graph is not differentiable, and it says to give reasons. And our reasons are going to, there are 3 reasons I'm looking for. We are not continuous, we have a sharp turn, or we have a vertical tangent. See what you can do here. Find all the places we are not differentiable and give reasons. Let's see, I'm going to start with x equals -1 because there's a sharp turn. Then I'm going to go to x equals 4. Don't say jump when you're talking about why we're not differentiable. Give the more general, we're not continuous. Then looks like there's another sharp turn happening at x equals 8. So it looks like -1, 4, and 8. Oh, actually, maybe you found one more. Hopefully you found one more. Looks like at x equals 11, I've got a vertical tangent going on. Sorry, this is a little bit messy. But there are 4 places we were looking for. X equals -1 because there was a sharp turn. X equals 4 because we weren't continuous. X equals 8 because of the sharp turn. And x equals 11 because of the vertical tangent. One more of these. 36. 2 parts here. Part A, where are we discontinuous and why? Your reasons for why will be things like there's a hole, there's a jump, there's a vertical asymptote. B, where are we not differentiable? That's where you're going to give our 3 new terms. We're not continuous, we have a sharp turn, or there's a vertical tangent. Try part A. Where is G discontinuous and why? Okay, well, at x equals -2, there's a hole. X equals 0, there's a vertical asymptote. And 1, 2, 3, 4, 5, x equals 5, there's a jump. Next, where are we not differentiable? Well, first of all, I feel like 3 places where we're not differentiable should be really, really easy. Because every place where we were not continuous, we are going to be not differentiable. So I'm going to say x equals -2, 0, and 5, because we're not continuous. Take a moment, find the other places, and give reasons. A little tricky to see, but it looks like a sharp turn at x equals -1. It actually looks like another sharp turn at x equals 2. So how about I talk about those as sharp turns, or cusps. And then I feel like, yeah, there's a vertical tangent. Those are definitely the trickiest ones to pick out. 1, 2, 3, 4, x equals 4 is a vertical tangent. There's one more thing I want to talk about with this. There's a theorem. Which says, if a function is differentiable at a particular point, it also has to be continuous at that point. If f is differentiable at x equals c, if I can find a derivative, if I can find the slope of a tangent line, that must mean that f is continuous at x equals c. If a function is differentiable, if I know I can find the slope of a tangent line, then that function has to be continuous at x equals c. As long as I'm differentiable, I'm continuous. Well, I think that should make a little bit of sense because we know that a discontinuity is one way I could be not differentiable. So if I am differentiable, I got to be continuous. That's kind of what it's saying. Couple things. The converse, going back to a geometry term that you learned about freshman year, of the statement is not true. If we're continuous, does that mean we're differentiable? Not necessarily. I could have a sharp turn, I could have a vertical tangent, that doesn't hold. Why this is going to be useful? Remember back in chapter 1 with our intermediate value theorem, we were trying to prove that a specific y value would exist, and we would start by saying, well, because our function is continuous and all this stuff. If we're given on the AP exam a table of values, they may not say our function is continuous. They might say the function is differentiable. If they say the function is differentiable by this theorem, we know that our function has to be continuous. So if we were using the intermediate value theorem, we could say we were told the function is differentiable, which implies it has to be continuous everywhere. That's all I have to say about this.